Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, so today we will continue our lecture with chapter 3, angle modulation, transmission and reception part 2. Okay, so in the previous lecture we have covered chapter 3 part 1. So part 1 actually covers from subchapter 3.1 up until subchapter 3.4, modulation index and percent modulation. So in this part 2, basically we will cover from 3.5 frequency and bandwidth analysis until 3.11, which is FM demodulators. Okay. However, for this part 2, I will be dividing it into two sections, part 2A and also part 2B. So part 2A, which is this video, it will cover only subchapter 3.5 and subchapter 3.6, while for part 2B, it will cover from 3.7 until 3.11. Okay, so the reason why I divide this part 2 into two sections is because part 1 and also part 2A is the I wanted you to focus more on part 1 and part 2A because it covers on the basic concept of angle modulation. So part 1 and part 2A it includes the theoretical part and also the calculation part. Okay, and for part 2B it is more on the theoretical part, explaining on the transmitter, receiver, FM demodulators, and so on. Okay, so this video is for chapter 3, part 2A. So we will continue with chapter 3.5, which is frequency and bandwidth analysis of angle modulated wave. So if we basically if we compare angle modulation and also amplitude modulation, angle modulation is much more complex compared to amplitude modulation that we have learned in chapter 2. Okay, so why we say that this angle modulation is much more complex is because this angle modulation, it reduces an infinite number of side frequency. So since it reduces infinite number of side frequencies, automatically it will has an infinite bandwidth. Okay, where each side frequency is displaced from the carrier by an integral multiple of the modulating frequency. So if you compare with amplitude modulation, okay, so I will open the slide for chapter 2 just for recap. So this is the frequency spectrum for amplitude modulation that you have learned in chapter 2. Okay, so for the output of the amplitude modulation, you look at here, you have a carrier frequency in the middle and you only have one side frequencies. Okay, so this is the upper side frequency and this is the lower side frequency. Okay, so you only have one pair of side frequency compared to this is if you have one modulating signal. Compared to angle modulation, okay, so even though you only have one modulating signal, you could have several number of side frequency, not just one side frequency. Okay, so the side frequency in angle modulation is actually depending on your modulation index. Okay, so for example, if modulation index, later on I will further explain this. So for example, if you have a modulation index equals to 1, okay, so automatically you will have 3 pairs of side frequency. Okay. So I will explain that one in the following slide. So if you remember this formula, okay. Okay, so if you remember this formula, this is the formula or the equation for the angle modulated wave. Mt equals to Vc cos omega ct plus m cos omega mt. Okay, so I already introduced this formula in chapter 3 part 1. Okay, so this is the output equation for angle modulated wave, where Vc here is the carrier amplitude. We have m is the modulation index. Okay, but based on the above equation, we do not know the individual frequency components of the angle modulated wave. Okay, we don't know what the exact component existed in the angle modulated wave. Okay, so in order to determine the exact component in the angle modulated wave, we can use what we call as the Bessel function identities. So equation 9 here is the Bessel function identities. Okay, cos alpha plus m cos beta equals to this equation where j and m is the Bessel function of the first kind. So what you need to do is that if you apply this equation 19 to equation 12, so this is the equation 12. So you will get equation 20, which is mt equals to Vc j n m cos omega ct plus n omega mt plus n pi over 2. Okay, so to apply this equation, you know that cos alpha plus n cos beta is equals to this. Okay, so the previous equation, equation 12, you have Vc cos omega ct plus n cos omega mt. So basically, you know that this is cos alpha plus m cos beta. Okay, so this is alpha and this is beta. So you will get this equation, okay, cos omega ct plus n omega mt plus n pi over 2. And then what you need to do is that you need to expand the equation because you have the summation function here. So if you expand equation 20, so you will get this equation. Okay, so this is the output equation for the angle modulated wave, the expanded version. Okay, so the equation is mt equals to Vc j naught plus j1 minus j1 plus j2 up until j and m. Okay, so m is the modulation index, Vc is of course the carrier amplitude, j naught is the carrier component, and this one j1 j2 up until jm is the side frequency. Okay, so if for example your equation is up until j1m and so on until this part, is meaning that you only have one set of side frequency. Okay, but if your equation has a component of j up until j6m, so it means that you have 6 sets of side frequency. So in other words, angle modulation produces infinite number of sidebands depend on the modulation index. Okay, so how can we know that how many number of sidebands exist, okay, in the angle modulated wave? So first of all, you need to determine the modulation index. Okay, then you need to refer to this table. So this table we call as the Bessel function table. So if you look at here, you have the modulation index, and this you have the carrier, and this from J1 up until J14, this is the side frequency. Okay, so for example, if you calculate and you found that your M is equals to 1, okay, so what you need to do, you refer to this table. Okay, so M equals to 1 is this. Okay, so you look at here, J naught is the carrier component. So the amplitude for the carrier component is equals to 0.77. Okay, and then you have J1, J2, and also J3. So this actually means that you have 3 sets of side frequency with the amplitude of 0.44, 0.11, and also 0.002. Okay, so for example, if you want to draw the spectrum, the frequency spectrum for this one, for M equals to 1, so your frequency spectrum will be something like this. So this is your carrier component. Okay, and then you have 3 sets of side frequency. This is 1, 3. Okay, same for the other part. 1, 2, and 3. Okay, so the amplitude of this sideband is, the amplitude for this is 0.77. This is the carrier, and then this is the amplitude is 0.44. Same for this one. This is 0.11, and this is 0.02. Okay, same for the other side. The amplitude for this side band, side frequency, is 0.44, this is 0.11, and 0.02. Okay, so the number of side bands, it depends on the modulation index. Okay, so you can see that the higher the modulation index, okay, the more side bands you will have. Okay, for example, you have modulation index equals to 10, you will have 14 sets of sidebands. Okay, so when you have 14 sets of sidebands, you will have a system with a higher or a bigger bandwidth. So this is the Bessel function. Okay, this one is what we call as the Bessel function curves. The function is actually the same as the Bessel function table, but if, for example, in your midterm test, you are given this one, not the Bessel table. Still, you can determine the number of uh, set of sidebands exists in the system. Okay, so for example, this is M equals to 1. This is the modulation index. This is the sideband. So if M equals to 1, okay, so you just draw the line here. M equals to 1. Just draw the line, okay, and you can know the amplitude or the value for J naught and also for J2, J1, J2, and up until Jn. Okay, for m equals to 1. But using this curve is not that accurate as compared to this Basel table, because from the Basel table you can get the exact value. Okay, but for the Basel curve is more like an estimation. So conclusion from the table and the graph, what we can conclude that is that for m equals to 0, modulation index equals to 0, it will produce 0 side frequency. Okay, so you look at here, when m equals to 0, you only have the carrier component j naught equals to 1, and you don't have j1, you don't have j2, and so on. So meaning you don't have any sidebands. Okay. And we also know that the larger the modulation index, the more sets of side frequency produced. This is what I explained before. The larger the modulation index, the more the number of side frequency produced. Okay. And then values shown for Jn are relative to the amplitude of the unmodulated carrier. Okay, so basically the number of side frequency pairs uh, is affected by the modulation index, and this modulation index is affected by the modulating signal. Okay. So as the modulation index decreases below unity, okay, below unity meaning below 1, the amplitude of the higher order side frequencies rapidly becomes insignificant. Okay, what it means by insignificant is that the amplitude is less than 0.001. So that's what it means by this statement is that as the modulation index decreases below unity, below 1, okay, as the modulation index is below 1, you can see that the higher order sideband is insignificant. Okay, that's why you don't have the higher order sideband. We call the sideband as significant when the value is 0.001, bigger than 0.001. If lower than 0.001, we call it insignificant. So we just ignore the value. And then as the modulation index increases from 0, the magnitude of the carrier will decrease, and the negative values for Jn simply indicate the relative phase. Okay. And this is what I explained before. Side frequency is not considered significant unless that Jn is bigger than 0.001. And lastly, as the modulation index increases, the number of significant side frequency increases, and the bandwidth will also increase. So next, let's look at the bandwidth requirement. So we know that based on the Bessel table, we know that angle modulated wave consumes larger bandwidth compared to amplitude modulated wave. Okay, so the bandwidth of angle modulated wave is a function of the modulating signal and also the modulation index. Okay, it is affected by modulation index and also the modulating signal. Okay, so basically there are two ways to calculate for the bandwidth for angle modulation. Okay, so the first technique is by using the Bessel function. Okay. So if you calculate the bandwidth using the Bessel function, this is the formula that you need to use, which is bandwidth equals to 2n Fm hertz. Okay, so Fm is the modulating signal frequency, and here is the number of significant sideband. Okay, how to determine the number of significant sideband? You need to refer to the Bessel table. And then the second technique, okay, is the Carson's rule. Different from the Bessel function, Carson's rules is more is an estimation. Okay, it is used to estimate the bandwidth regardless of the modulation index. Okay, so for Bessel table, Bessel function, you will have the table. Okay, so for different modulation index, you will have different number of significant side band. Okay, but Carson's rule is more to estimation regardless of the modulation index. So what Carson's rule proposed is that it stated that the bandwidth is equals to 2 delta F plus Fm. Okay, so delta F is the peak frequency deviation. Fm is the highest modulating signal frequency. Okay, so for Carson's rules, the formula that you need to use is this one. B equals to 2 delta F plus Fm. However, for a low modulation index, we know that the modulating frequency is much larger compared to delta F. So what we can do is that since Fm is much larger than delta F here, what we can do is that we can ignore delta F. Okay, and your bandwidth will become B equals to 2 Fm. This is for low modulation index. But if you have a high modulation index, okay, the delta F is much larger than the modulating frequency. So since Fm is much larger than delta F, and since delta F is much larger than Fm, you can ignore Fm and your equation will become bandwidth equals to 2 delta F. And this is valid for a high modulation index. Okay. So if you look at here, Carson's rule approximate, okay, it only approximate and it gives a narrower bandwidth compared to the bandwidth determined using the Bessel function. Okay, so even though it gives a narrower bandwidth, but it will but it will give a poorer performance compared to the system which uses the bandwidth using the Bessel table. Okay. So next is the deviation ratio. So the deviation ratio is basically the worst case modulation index. It's a modulation index, but for the worst case scenario. Okay. So the formula for deviation ratio is dr equals to delta F max, which is the maximum peak frequency deviation, divided by the maximum modulating signal frequency. So now let's look at this example. Okay, so the questions, example A, determine the deviation ratio and bandwidth for the worst case modulation index for an FM broadcast band transmitter with a maximum frequency deviation of 75 kHz and a maximum modulating signal frequency of 15 kHz. Okay, so you know that this is delta F. This is delta F max and this is Fm max. Okay, so the deviation ratio is delta Fm max divided by the Fm max. So you will get the deviation ratio equals to 5. Okay, so now you want to determine the bandwidth using Bessel table. Okay, remember the division ratio is basically the modulation index. Okay, however, but it is a worst case modulation index. So now your modulation index is equals to 5. Okay, and you want to calculate for the bandwidth using the Bessel table. So the equation for bandwidth using Bessel table is P equals to 2n Fm. Okay, so your Fm is 15 kilohertz. Now you need to determine the number of significant sideband using the Bessel table. So now let's look at the Bessel table. So n equals to 5. N equals to 5. For n equals to 5, you have J1, J2, J3, J4, J5, J6, J7, and J8. So this means that you have 8 pairs of sidebands. So now your n is one. Your n here is actually equals to 8. So B equals to 2 multiplied with 8 multiplied with 15k, we will get the bandwidth equals to 240 kilohertz. So now let's look at example B. Okay, for a 37.5 kilohertz frequency deviation and a modulating signal frequency Fm equals to 7.5 kilohertz, the modulation index is M equals to frequency division divided by Fm. So you will get M equals to 5. Okay, so remember, previously we have referred to the Bessel table that when M equals to 5, the number of significant sideband is 8. So using the same formula, P equals to 2n Fm. Okay, you put in the values, you will get the bandwidth now is 120 kilohertz. Okay, so you look at here, example A and example B, even though it has the same uh, value for the modulation index, however, the bandwidth is different because this one is for the worst case scenario for the widest bandwidth. So the widest bandwidth is equals to 240 kilohertz. This one is not the worst case scenario, so the bandwidth is 120 kilohertz. Okay, so this is what I explained before. Although the same modulation index was achieved with two different modulating signal frequencies and amplitudes, two different bandwidths were produced. Okay, and the widest bandwidth will only be produced from the maximum modulating signal frequency and maximum frequency deviation. So the same condition also applies in the case of using the Carson's rule. For example, instead of using the Bessel table, you want to calculate the bandwidth using the Carson rule. So this is the formula for the Carson rule. Okay, so for the worst case scenario, you'll be using delta Fmx and also Fmx. So your bandwidth, you will get 180 kilohertz. If you compare with using the Bessel table, this is 240 kilohertz. Okay, so there's a slight difference between for the bandwidth using Bessel table and the Carson rule. So I already explained before that Carson rule will give a value, the bandwidth value that is smaller than using the Bessel table. However, the performance using the Carson rules is poorer compared to using Bessel function. Okay, so basically that's the end for chapter 2, chapter 3, part 2A. Okay, so next, in another video, we will continue with the chapter 2, part, chapter 3, part 2B, which is 3.7, subchapter 3.7, up until subchapter 3.11. So thank you.